Hello everyone. So this week, let's start with what what we have done so far. Let's just review that and think about what we have to achieve today. And it's probably gonna be the helper that I was talking about previously. So we have the low-level helper that can allocate pages. I mean, it's not going to allocate pages, it's just going to manage the pages, the actual physical pages, and we can ask it to give more pages for us. That's all it's going to do. Now, what we have to come up with is the high level helper that will run on top of this page allocation helper. Okay, let's first of all let's just start by understanding what exactly this helper might look like. Let's say let's say high level physical page allocator. No. What is on top of physical page allocator? Callback, call stack from top of from let's say kalloc to the physical page allocator. If we know this call stack, we can check the actual implementation of some of the functions and see what we have done and what exactly we could possibly do here. So kalloc gets into unallocated. Okay, in Linux it will be like kmalloc, and we have slab allocator, and we have alloc pages, and we have this. So body allocator is the lowest. Okay. Block of 2n pages splits the in physical pages. Okay. This is where we do virtual page management. Get page from. Okay, so we also have to think about virtual page management. But virtual page management should be done by the process, right? Because malloc is supposed to do the virtual page. What is malloc do? Malloc, I guess, is just going to use. Malloc is just going to keep track of the virtual memory, and it's going to use my mmap to allocate new virtual memory or to get new virtual memory. But after that, what happens? So let's see. In Linux, explain from the kalloc flow. Do we start? What? Sorry. What does it mean to get something from this helper, and what does it do? Let's understand, try to get an idea of all the functions below this. Okay. Oh, I know, you fucking piece of shit. Okay, so it's kmalloc, and what it does is kernel malloc, and it's true. The allocation stack uses which calls allocation page, which calls get page from free lists, and which uses and finally returns the physical page frames. No, I want to know what exactly kmalloc will get. It will get a pointer to some free memory. In this explain what every function will take as input and explain what it will give as output. Okay, so kmalloc is going to take the number of size requested. So let's say we have an object, we just give size of, and we expect that to be given, and we also can give some memory allocation flags. That's not anything for us, and we get a pointer to a virtual memory address. So it's going to be something within this the virtual base. Okay, that's good. That's good. This points to the allocated. Okay, that's fine. Now let's get to the next helper. It's not a single function, it's the function. Input will be a cache, and GB flags and node. Okay, I guess node is just the I guess RAM has different types of nodes, and one on the top will be used, something like that. I have tried to understand RAM once. It was a really long back, so yeah, there's some course stuff like that. I don't know anything about it. I don't know anything about it, so maybe we'll have to understand it later. But as of now, let's just assume it's something. But I think it's just the nearest node because there is some performance thing. So whichever node is the nearest will be allocated, something like that. I don't remember. I mean, we can check nodes in RAM. Yes. There are node names. We can also print those and see what exactly we are using. No, not this. Nodes in RAM. RAM internals. Not the RTL level. I don't need the RTL level. I don't care about RTL level. But there is something called a node inside, and well, we'll just fucking ask this thing. Mm-hmm. Numa node locate from. Aims to minimize the memory latency. Yeah, I know, no, because it's something about latency. That's how I remember it. Because it's just about whichever node is the nearest, we try to use that. Something like that. I remember that, but I don't remember it fully. Uh, mm, memory. What is Numa? Let's just go here. System cell of the Numa system is collected to other sort of interconnects. No, sketchy, coherent Numa. Next, called nodes. Linux maps the nodes onto physical cell of the hardware platform, abstracting away some of the details for some architectures. As with physical cells, software nodes may contain zero or more CPUs. Okay. For some architectures, hide any node representation a physical cell that has no memory attached. Okay, I didn't get anything. Well, we'll still continue to look. Linux consists of independent memory management system complete with free page lists in use. Says that DMA zone list, because some nodes contain multiple zones containing abstractions on top of RAM in Linux. Paging, leave that, we know that. Caching mechanism, these types including stack memory, local memory. For resource, you fucking. I didn't get anything out of it. Nope. Nothing works. I guess I read it somewhere in some book. I don't remember, but there's a definite proper explanation of how it works. But I could just read this from the beginning and understand the piece, but that would be so time consuming, so I have to find something quick. How do we do that? Improve locally, architectures does not. Some kernels don't want to tolerate typical models. Numa memory ID. Can we split this even more? Is that something we could do? Okay, we won't be able to do that. Why do we need Numa nodes? We need to address memory access bottlenecks in large-scale multiprocessing. Traditional symmetric multiprocessing due to the contention of shared bus system. As the number of processes increase, the demand for bandwidth grows, and a single shared bus becomes a performance bottleneck. Okay, so yeah, there is one RAM and it needs to be connected through some bus. And yeah, if we have multiple cores, everyone has to go through this bus to access the memory, and it's going to be some sort of contention zone. Okay, so solves this by organizing processes, and what is it? And memory into separate nodes. Organizes processors and memories into separate nodes, each with its own local design. Allows for scalable memory bandwidth as processes primarily access their local memory, reducing latency and improving overall stability. Need for data to travel over a shared bus. NUMA enables systems to scale. But what the fuck do you mean by local? Because there's no fucking thing as local. I think we need to create. Good to see you. Fuck you. Explain how this works. Like, what exactly? It's the flow. Also, how is... Maybe we will just start with the flow and then we can think about the rest. Multiple nodes, each nodes containing group of CPUs. Okay, a chunk of memory local to the node. Okay. High speed interconnects. Is this physical? That's the first question. Okay, let's just move on. When a CPU needs data, it first checks it's in its own local memory. Okay, memory controller. So it seems like it's a physical thing. Data is returned with low latency and high bandwidth. The data is not in local memory. The request goes to another node. Check local memory, local hit, local miss. Okay. Command to check the NUMA in Ubuntu in Mac OS, because I have a fucking Mac. Oh, okay. The fucking map does not have that. But whatever, it's just so NUMA goes so NUMA memory. Let's just confirm this one thing. NUMA memory controller is a physical thing. Okay, so that explains it. So it's a fucking physical thing. Memory controller is a physical hardware group. Node contains a group of CPU cores. A memory controller, a chunk of physical memory. Okay. Okay. Is it part of the RAM? No, pneumo control is not part of the RAM itself, it's part of CPU. Okay. System is logical. Just a minute. Translate. So what did you mean when you mentioned that a particular node gets a small amount of physical memory? I mean, if RAM is not part of this, then even this small amount of physical RAM should be taken through some bus. Has directly attached. Okay, so they all have separate bus. Okay, has X amount of, I don't mean it's built inside it. Each has directly through dedicated. This is the key. So those pneumo nodes are directly dedicated. They have direct channels, so they don't have to go through the central bus. Okay. Okay. Then is it even possible to not have a memory? To have missed that? Because as you mentioned, it has separate channel to access the RAM. Okay, those are the catch. When a CPU misses a memory request, the memory controller checks, is this address inside this node's RAM region? But what's the point? Why not give everyone full access to RAM on a separate channel? Why restriction? Why do we restrict it to a small region or whatever region? What's the point? What was the reasoning behind that? HDMI has restrict time dedicated. Okay. Oh, so every CPU needed. Ah, okay. So RAM is separate. I guess it already has a different um, channels. Hmm. I knew the there's some bandwidth difference in RAM. I didn't know that there's also channel difference. So, what's the current best RAM channel size? Mm, channel width is 64-bit. That's fine because almost every OS is 64-bit. So there's no point in increasing that. But what is? Okay, let's visualize it. Let's see if we can fucking understand something. Okay. So the total RAM is segmented into channels. Okay, so the total RAM capacity is not divided, so the bandwidth is divided. Okay, yeah, there is some latency difference. So that latency difference is separated into different channels. Okay, RAM sticks belong to specific channel. Okay, so the physical memory, physical RAM is also separated. 16 GB channel 0. Mm, mm. Okay, perfect. So now we at least know a little bit of what is a pneumacore. Pneumacore is just something that is assigned to the particular current core, whichever the process is running on that core. It that core has its own Numa number, Numa ID, and that ID has access to certain channels that can be directly connected to the RAM, and that is what we mean by improving performance. And let's come back to our initial thing, that is the second helper, and this helper is the slab allocator, and it is gonna take Numa node as the input, which particular node you want to allocate this particular. We are not gonna implement these things, but it's good to know. Return, and this is also gonna return a virtual address, and it allocates a new page. If the cache is empty, so let's just always assume that cache is empty. Same pages for Kmalloc. Sizes, same flags. Power of 2 pages. Order 0, then it's 1 page. If you want to order 1, then you get 2 pages. Return a structure to the page pointer. Represents the first page of the allocated block. Okay. Okay, it just forwards to this here. We tried in different zones of memory, normal or DMA. DMA, I guess it's for direct memory access or something. For, I guess it's only used by devices. And we also give the number of pages we want. And it's also going to return the same struct page. And we have to see what exactly this object is going to have. This is one thing that we care about, because we are not going to care about nodes, and we are not going to, at least in our version, we are not going to care about nodes, and we are not also going to be caring about zones. Okay, And this is finally gonna call the body allocator. Even here the return is the same. It's a struct page object. For conscious, okay. So yeah, finally everything is going to return a page. Then what's the point of kmalloc? Okay, kmalloc allows us to like hide all these details. But in general, calling kmalloc is just finally gonna resolve to ordering a new page. And now we know that even if we just gonna call kmalloc, finally we are just going to allocate new pages, and we keep returning page struct page. We are still returning struct page, and this is where we use the struct page. And kmalloc does one thing that I guess it's going to return a virtual address. I mean, every page is just the range of virtual address. So I guess it's just the top of the page. Every other helper is going to return a struct to the page, and but this particular helper will actually return the top of the page. I mean, every page has a range, and it's just going to give the top of that range. Okay, now let's just understand the struct page, because we might need to implement the same, because that will be useful. Struct page, give me the fields, yeah, fine, and usage in Linux. Okay, it's gonna be heavily overloaded. What we have? We have, I mean, we can leave out lots of information. We care about okay, we also have to have a pointer to the next page. We have a reference counter, so we know if this page is used or not. Who uses this page cache, virtual memory, IO system, slab? Okay, I still don't understand what exactly do we need from here, because let's go back to our R allocator. R allocator is just going to if we, where's the main helper? Where's it? If we call it, if we call allocate mem of 200 bytes with bitmap. Then what is our allocate memory written to definition? Where the fuck is the definition? Where have I defined it? Fucking. That's not good. That's my allocate mem. There's no allocate mem. Oh, it's here. It's going to, if it's less than that, we just set bitmap for that particular index and we return 1. Okay, we are returning the number of pages we have allocated. But that's not enough, right? Because we also need, because if I call this helper in my main, in my k main, let's say I get how many pages I have allocated. That's fine, that's good, but still I also want the actual top of the page. That's what we have to write code for today. So let's call it kmalloc. I think it will be good. Let's call it kmalloc. And it's going to return. Do we want to create a new structure that will represent a page? Maybe it will be useful because we do have a bitmap. No, bit index. And what is our bit index 2? It's just going to show the index within the bitmap, but can we get it? Okay, I have already allocated that. I am passing bit index, so I will be able to read it. Allocate mem. So it is going to, we can pass a bit index to it and we can get the actual index within that, and we can get the total number of pages that are allocated. So if we have the starting and we have the total, we can count and see, we can do arithmetic operations to find out or figure out the possibilities. Okay, that's fine, but what about the actual, what does it mean? Because let's say I have allocated pages from 17 to 20. What does that mean? Now, what exactly do I get? I have just some index within a bitmap, and conceptually we know that it represents a page and it is it has been allocated. Now what page does it represent? That will be the question. 17 is going to represent which range? And that's also a simple math because as we know, every page is 496 bytes of size, that is 4 KB. So it should be let's just try, what's it, decimal to hex, I guess, to hex. And if we go here and if we type 496, and this is the hex number, so the first page's range is 0 to 1000. And let's just take some notes because it would be easier to visualize it later. So we are returning the total number of pages that are allocated, and also the number of the bit index within the map. I guess that should be good because if we have that information and we have already set it to true. Wait, also let's understand what we do inside bitmap. We find a free node, we increment, keep incrementing t, and okay, and also bit index is an array of bit index, so we have bit index for every if there is 3, let's say we allocated 17, 18, 19, then we'll have 3 indexes, 3 in bit index. Okay, that's good, that's good. So example, let's say we allocated 3 index, 3 pages, then 17, 18 and 19. Our result will be an array of bit index. So we'll have bit index of for 17, bit index for 18, and we'll have bit index for 19. Okay, so this will be the output, and I think it resembles what we actually need, because as we learned from what Linux does, Linux is just going to, in the end, its body allocator is going to keep track of different pages, and it's just going to what the fuck, and every helper is just going to keep returning structure structure, that's the page, and every page will be finally be returned as a kernel virtual address, because page is just a small block of virtual addresses. So we just return the top of that sketch kernel virtual address. So I think it somehow resembles this because we have a small algorithm that can return us a set of pages and their indexes. Now we also have to, and our challenge would be what exactly is the starting address, and to calculate the we can easily calculate it. So to calculate the starting address of a page, all we have to do is that, because is it possible? It should be possible, right? Because um, it's just a page. No matter where it is, it's just a page. But it's a physical page. Ah, that's one difference. Because here we written a kernel page, kernel virtual address. Ah, okay. See, it's still possible. It's still possible. Let's think. Let's think. Mm, it's a physical. Let's just do the finish up this calculation. So if we have written 17th page, then as per calculation, all we have to do is I guess 4096 into 17. This should give, because first index is 0 to, let's just frame it. So it will be 0 to 0x 02 0x 100. So this is the range. So the second index would be G0x 1. I think it will be 002 2000, and it's going to keep on going. So the 17th index would be what it would be, what I mean, we can keep it as decimals, so it will be easier to calculate. That is 0 to 4096, and then it would be 409897 to what's into 2. It's 2, and it's 1819, and then there's 1, and there's 1 here, and it's 4. I think this is correct. I'm not sure. I just did the math in my fucking mind, so it might be wrong, but still. So all we have to do is, I think, we just have to, because it's just a multiple of 496 now. So 4096 into 17 should give us the output, possibly. Let's check. 4096 into 17. It's some big number, and we can also try to convert this. I think it's correct. Maybe 0 to 496 is the first 1 into 496. 17 into 496. I think it's correct. So we would be be in 0x 10,000 to this. I hope I'm correct. I don't know. I think I'm correct. I think this is how it should be. And now we have the physical address of the page that we just allocated. And what does the new helper do? Let's just write a intermediate helper, because we also need to do some mapping, because we need to update the page tables, because this is a physical memory. We need to get the virtual address of this physical. I think it's straightforward. We don't need much calculation, because we know that, because I think, yes, because because this is how we are taking the virtual kernel base is just this. So if we want 110, we just add 4 f's in front of it, and that would be the um, virtual kernel memory for that physical kernel memory, because we are doing identity mapping, at least for the final bits. I mean, we are literally doing just identity mapping. So I think there isn't much to do, but it would be nice to add a helper function that we can use to just add the mapping. What I'm trying to say here is, let me just write it down. It would be far simpler, because let's say we have this physical address. This is a physical address. We need to map this to VA, that is, let's say 0x 1 2 3 4 1 2 3 4 and 1 2 1 2 and 3 1 1 2 3. So this is what our virtual address would be, because we have it as this, and it will be identity mapped to the physical memory. This is fine, but we also have to update the page tables, because right now page table entries does not have an entry for this. I guess there's no entry for 111, because I think right now, what entries do we have? It must be, right now we have entry for 8,000 and 8,000 something. These are the two mappings we have. We do not have any other mapping. So we might need to update this. So if we write a helper, that will just take a physical address. It just has to take the physical address, and it has to create the mapping if it's not present. I think it's fine. Yes. No, it's going to take a virtual address and it's going to map it to. No. my page allocator, my page is going to give the physical memory, not the virtual memory. So if I have a physical address, I can by adding four F's in the front, I can say that that's the virtual address. But now I have to check if that virtual address has a page table entry. Okay, now it makes sense. Okay, so for the VA, so whenever we access this particular VA, there will be a mapping to this. And yeah, that's good. I guess it's this is what we want to achieve, and it's good. And how long? Okay, we still have half an hour. Half an hour. Let's just try to finish this helper then. Let's write. Okay, what do we write? What does this helper return? It returns a VA. So what does VA mean? What's the type of a VA? Okay, this is, it's just going to return a void pointer. It's going to return a void pointer, and the name will be kmalloc, and its input is going to be uint64, and VA address. No, this is a high level. No. This is a high level thing. So all we have to do is it just has to return allocate mem. Maybe we can improve this allocate mem thing, but let it be there as of now, because we need that mapping, because only with that mapping we know what are the things are actually used and what's not used. And we know the size of it. Now we have to allocate a bit index. And we can call this why did I even remove that? Total allocated equal to this, and it's just going to take mem and it's going to take size that we can just pass down, and it's also going to take the results. Okay, now we have the total number of pages allocated. and the index bit. So we can do is, what we can do is for total allocated, we don't need any initialization. We just check total allocated is, no, we need I. Oh fuck me, humans. How do I do that? I fucking forgot. Oh fuck it. Humans 64T I less than total allocated and plus plus I, and that should be good. Now we can index into that array current bit index current equal to rest of I. No, we also have the bit index. Now we know the, I think we only need the top because we need contiguous blocks. Okay, then I don't think we need this. We can just use, we take the 0th index, and we have the 0th index, and we need to convert this 0th index into a physical address. How do we do that? We need to do this. 17 means 406 into 17. So all we have to do is uint 64t index equal to current dot index and uint 64t pa is equal to 4 index into what's that, 4096. This is our page size. Maybe we can keep it as a defined value. If we do this, then we have the physical address now. What else do we have to do? We have the physical address. Now we also have to convert it into virtual address. So what we can do is uint 64t va equal to that's a simple bitwise operation. All we have to do is take one. No, we have to FFFF the first 4 bits. We can do that. It's simple. All we have to do is PA and 0x 1 2 3 4 and 1 2 3 4. No, that's not how it works. It is. Wait. We can 1 2 3 4 and 1 2 3 4, and we can R it with we shift our what can we do? We need to shift bit one all the most significant bits, and we have, let's write an example 0x100. We need to convert this into 0x fff 1 2 3 4 1 2 3 4 1 1 2 3. We have to convert it like this. We could simply do this and it would be like this. No, we are ANDing. If we AND it, both side needs to be this. So I guess we just R it. It should be done. Is it correct? We have FFFF. We are R'ing it with whatever that's in the front. We should get this. I think it's correct. Maybe we have to shift something. No, I think it's correct. Now we need to write one helper that's going to allocate it will be like bool allocated equal to allocate. No, we can call it as map page, and it's going to take VA, and then finally we can return VA as void pointer. I think it should work. This is what we wanted to do. We have bit index. We want to allocate some memory, and it's going to return bit indexes, and it's going to return the total number of pages that are allocated. And we know we know that these pages are going to be next to each other, so we can just take the first index and we can multiply it by the page size, so we'll get the physical address. And if we FFFF the initial bits, we'll also get the virtual address. One more thing we need to make sure is that we need to assign page table map page table entries for that VA. Entry for that VA. Page entry. Let's say page table entry. I think it should be good. We also have to do one more thing. We have to allocate multiple things, so it will also take the total allocated, so that way we know how far we have to allocate, because we start from this index, but how long, because one page and table entry is just going to be 4, so we need to allocate 4 page table entries, or maybe 3 page table entries. Okay, so we have the function signature, And we have allocated the high level KMLOC. Now only thing left is this. I think it looks good. Nothing much. Yep. So let's just recap what we have done today. So previously last week we already wrote the allocate mem that's going to use a bitmap array to keep track of the actual pages, and they are going to be 4 KB page size, and it's going to take a bitmap to keep track of everything, and it should work just fine. Today, our goal was to understand how we can use this low level helper to get the actual virtual memory. And in our case, as you can see, we need a kmalloc, and as we saw from the Linux example, all we have to do is just return pages and finally convert it into a physical virtual address. So our helper is going to give us the pages. Now we can use some arithmetic operation to get the physical address, and we work on top of virtual address. So we convert it into a virtual address, and then we need to make sure that this virtual address has a mapping to a physical address. And we are just going to do identity mapping, so we don't have to care about that. But in case we don't do identity mapping, then there will be an issue, because this PA to VA operation may not work, because we don't know what this VA will be mapped to. It can be any PA. But in our case, it just works fine, because we don't care. We just identity map. So we have a physical address. We can just add 4 FFFs to get the virtual address. And we call a helper that is going to actually allocate this, no, actually add this page table entry, because these page table entries should be added to which, I guess it's a register. Yeah, this register, it's TLTC EL1, I guess, I suppose. Yeah, it holds the table, and we have to probably will just be copying some of these code and create a helper function instead of hard coding it like this, and it should be good. I think so. Yeah. Yeah, let's we can do it tomorrow. I guess this is enough of what we have done today. I hope everything is clear, and I hope that whatever I did was fucking correct, and I believe it's correct, because this is what Linux is doing, and we are maybe doing a little bit of a shortcutted version of that, but it's still fine. It would still work. And yeah, bye bye guys. We'll see you tomorrow then. Bye. Have a good day.